This video demonstrates using Kornucopia ML for importing and processing transient data recorded by the Spectral Dynamics Vidas high-speed test measurement system. Kornucopia ML for use with MATLAB is truly the horn of plenty, with its large number of tools to help you analyze real-world, complicated data. These capabilities are applicable for the analysis of both physical test data and simulation results. In this video, we will concentrate on Kornucopia functionality for importing and processing transient measurements created by the Impax-SD software that runs on the Spectral Dynamics Vidas measurement system. Consider a typical scenario where you are making several high-speed transient measurements with this system. For each test event, the measurements are stored on several channels containing different types of sensors. In the example below, accelerometers, strain gauges, and laser displacement sensors are being utilized. Here we are in the Impax-SD software. We have set up a test with 7 sensors. Within Impax-SD, we can also define relevant metadata for our test. For example, the test description form has a few high-level fields that can be populated, and the project description form has a number of entries that can also hold useful testing parameters and comments. Once our test is set up, we record a measurement with the Vidas system. Looking at the data folder in Windows, we see that for each test event, the raw data from the 7 sensors is recorded in individual hybrid binary files, 1 file per sensor. It is noted that the files of a common test event share a common file extension, defined as the event number. Since we are looking at our first test event, the extension is 001 for all of these files. We now switch to the MATLAB environment and use Kornucopia to import all of these data files from the single test event. Kornucopia has 3 specific functions that import Impax-SD data files. Here we use the SD-Impax import function. This provides an easy-to-use GUI interface to select the data folder, pick which events to load, and then provide several options for how you want to map the Impax-SD meta information into Kornucopia's tabular K-units data type. Once we hit the Process All Files button, Kornucopia quickly loads all the data into MATLAB, storing the results in a MATLAB table, which is now being displayed with Kornucopia's var viewer function. From here we see there are several types of items being parsed and imported, including some handy items like listing the raw sampling rate and a check for signal clipping. Next we show that much of the common meta information is stored in the column Common Info, which itself is a structured variable showing fields consistent with the meta categories in Impax-SD. Now we show what's in the project field, a variety of items. Kornucopia adds an additional view to the project's description form by interpreting it as a kind of table. This is stored in the Proj Summary field within Kornucopia. Let's now look at the raw sensor signals that were imported. These were stored in the SD raw column within the results table. The entity shown now is a K-units data type that holds a description at its top, the event number, along with both column names and units that were directly mapped and automatically imported from the Impax-SD sensor metadata. Here we isolate time and the acceleration columns into the variable accel. Because Kornucopia understands units, it knows how to properly integrate the acceleration data that was in units of g's, resulting in velocity for the 2 accelerometers in units of meters per second. Perhaps you prefer a different set of units for velocity, say inches per second. No problem. We simply use the convert method to transform the units and the data of the output to our desired units. We can also make global-like settings to control what type of units are returned during calculations in Kornucopia. The default units preference is the SI system, but we can easily pick from a variety of pre-made unit preferences, such as this one. Now recomputing the velocity from the acceleration results in units of millimeters per millisecond. Lastly, we demonstrate that Kornucopia also stores the Impax-SD meta information within the variable's user data property. This information is also carried through math operations like integration, so the velocity calculation that was made previously also has the meta information within it. For the user, this type of metadata handling means that you have a traceable workflow. If you send these variables to other colleagues via mat file, all of this information goes with it, not just a dangerous array of numbers only, but a fully described variable with column names, units, and related meta information. Returning back to the Vidas system, after a day's worth of work, you will likely have tens or maybe hundreds of events recorded, and a ton of data files to process. As seen, Impax-SD stores each of the sensor channels in a separate file, where the file extensions for a given test event are defined by the event number. Fortunately, Kornucopia easily imports and processes all this data, as we will now demonstrate. Back in the MATLAB environment, we use Kornucopia's SD Impax importing functionality to interactively select and import test events. The software smartly lists available event numbers from the data folder. You can then select all the events, or only particular events of interest. Kornucopia remembers your mapping selections from the previous use of the function, so we are now ready to process all the files. As demonstrated before, Kornucopia inputs the data into a table, which in this example now holds several rows, one for each event imported. You can think of this like a database with records, one record per test event. Getting to the sensor data for further calculation or plotting is quite easy as shown here. And here are a few simple commands to plot the response of sensor disp_z1 across all 6 events. Kornucopia's kplot function automatically labels the plot based on the column names, units, and other metadata that it knows from the variables. From this plot, we quickly see that a few of the events did not seem to record any response. Perhaps we have a sensor issue. As presented at the beginning of this video, Kornucopia has a variety of tools to process noisy and messy data, just like the data that is typically recorded in Vidas high-speed, transient test measurements. Additionally, Kornucopia works naturally with a large number of built-in MATLAB functions. Plus, there are over 120 Kornucopia advanced functions that span a variety of categories related to working with complicated, real-world data. When working with frequency-rich data that may come from a variety of sources, Kornucopia's suite of DSP and shock spectrum tools are extremely helpful. Kornucopia's powerful, yet easy-to-use tools for processing noisy data cover a broad range of needs. Utilizing these types of Kornucopia functions, you can turn your raw measurement data into meaningful engineering information. For our last demonstration, we show a typical example of importing and post-processing a number of Vidas measurement events using a custom script created with Kornucopia MATLAB commands. The script has a few collapsed sections that hold the code to perform all the work. Using the settings in this section, the user can easily enable and disable features of the script. We initiate the script by running the first couple of sections. The third section contains the SD Impax import call that we have presented previously. After selecting an event of interest, the code imports the data and does a variety of post-processing calculations. Running the next section directs the script to automatically plot the various entities, including raw data after it is adjusted to remove DC drifting, discrete Fourier spectrums, low-pass filter results, velocity derived from integrating any acceleration containing columns, and shock spectrum curves computed from the acceleration data. Remember, all of these quantities come from the calculations performed in the script. The plots are being presented in a nicely organized results workbook that is easily created with Kornucopia's kfig tab family of functions. Notice that the plots are all well labeled, including units. Additionally, relevant meta information from the test and a summary of shock results are presented in a highly organized fashion on the plots. Next, we rerun the read and process section of the script to add more events to our results. Because we have now loaded a total of 4 events, 1 previously plus 3 now, our pseudo-database variable db holds 4 rows with a large number of columns that include various computed results which are easily referenced and plotted as needed. Running the generates plot section once more allows us to select the newly added events and include them in the existing figure, which we had created a few moments ago. The script automatically adds 3 top-level tabs for the 3 additional events, and then under each new event tab, it creates the needed subtabs and plots for the relevant data. At the end of all the plotting, the script looks across all the events plotted and rescales plots of compatible quantities to the same scales for easy results comparison. Our figure now holds 48 plots of all the results. With Kornucopia's help, it is quick and easy to compare the quantities, such as strain, across the different test events. Perhaps you desire to dig a little deeper into the strain results of event 44. We can easily pop out the graph to make it full screen, or we can use this Kornucopia interactive feature to highlight one or more of the curves of interest. Maybe consider them for trimming, or just have the curves data extracted back into the MATLAB environment. As we see, Kornucopia has kept all the column names and units for the curve, and even its metadata, including some new meta information about the low-pass filter that was applied. Finally, we use the figure's Kornucopia menu to store the M script with the figure, and then use this menu to save the entire figure to a file, where all the advanced Kornucopia technology gets properly stored into the fig file. Remember, this fig file can be opened later in another session where all the results can be viewed in an orderly manner and any curves can easily be extracted for further analysis. You do not need the original source data for this to work because everything needed was stored in the fig file. By now you have seen that Kornucopia is the perfect companion tool for processing, plotting, and organizing your Vidas measurement data. With Kornucopia ML, you get faster data analysis with greater understanding, because you get to work with all your data, numbers, units, and text. This enables flexible and more accurate workflows, giving you and your team greater confidence in your results. There are tools to process messy and noisy data for solving important, real-world problems. With efficient plotting that has automatic labeling, you can quickly and clearly communicate your results. And our real-world template examples help you jumpstart your solutions. This is all supported with a teaching help system that allows you to learn more and grow your value. Kornucopia ML improves the speed, precision, and effectiveness of both you and your team.